Welcome back, everyone. So today we're going to cover a couple of a couple of simple things that actually can be quite useful. So first, let's start off with something called source transformation. And source transformation is actually really easy, really straightforward, but can be incredibly valuable, depending on the situation. So let's see what it is. Now we can kind of take we can take a voltage source in series with a resistor. And we can turn a voltage source in series with a resistor, and we can turn that into a current source in parallel with a resistor. Now, although this is the same circuit as what you would get with a Thevenin equivalent circuit, and this is the same circuit that you would get after performing a Norton equivalent circuit, don't get confused and think these are Thevenin or Norton equivalent circuits, although they kind of might as well be, because they are the same output that you would get from a Norton or Thevenin equivalency. So when you perform, when you're talking about a Thevenin equivalent circuit, you're performing the action of deriving a Thevenin equivalent circuit, and then this is what you would get. And when you perform a Norton equivalent circuit, this is what you would get after performing that procedure. So the result is the same, but let's just take this for what it is, which is a voltage source in series with a resistor. Anytime you see this, you can convert this to this very easily. And similarly, you can convert back from a Norton equivalent circuit or from a current source in parallel with a resistor. You can convert this back to this. So performing this conversion is very trivial to do. And in fact, if you want to convert this, all we have to do is perform Ohm's law on the voltage source over here with its given resistor. So the I over here is actually equal to V over R. And similarly, the V over here is equal to IR. So let's go ahead and let's just do a source transformation and convert some voltage source with a series resistor into this guy. So let's take a 10-volt source and a 2 ohm series resistor. And let's say what we wanted was a current source in parallel with a resistor. Now, the resistance is going to stay the same. R stays the same among these. And in fact, when you did your Thevenin and Norton equivalent circuits for the lab that we did last time, you saw that you calculate R the same exact way, right? So the R stays the same. In other words, we're going to get 2 ohms here. However, for I, we're just going to apply Ohm's law to convert into our current source. So in this case, 10 volts divided by 2 ohms gives us 5 amps. And that's all there is to this. This is identical to this from these 2 points. And similarly, we can just go in the other direction and just apply Ohm's law. So let's do another example. Let's take a 2 amp with a 3 ohm parallel resistor, and let's say that this didn't suit us in our circuit, and we saw this, and a voltage source with a series resistor would end up ultimately being more useful. And in fact, next class we will see that that can be the case, where this actually ends up being much easier to solve than this, and we'll see that next class. But let's just go ahead and say that we wanted to convert this into this. Well, the resistance is going to stay the same. Our parallel 3 ohms is going to be 3 ohms. And we just need to apply Ohm's law in order to get a R source transformation here. So in this case, V is going to be equal to I times R. So this ends up being 6 volts. Okay, so I think pretty straightforward, pretty easy, and it's just knowing when the situation calls for it, that it might be, that you probably need a little more experience to see when doing this source transformation is beneficial. So now that we know about this source transformation, and since we should have done the lab already, can anyone give me the values that they got for their Thevenin and Norton equivalent circuit from lab? You can call it out or type it into chat, but let me know from the lab. Let's start with the Thevenin equivalent circuit. I see 3 volts and 3 milliamps, 7.5 volts. Okay, so for the Thevenin equivalent circuit, there we go. Okay, someone said they got a VTH of 5 volts, and RTH was 666.66 repeating ohms. Sorry for having a repeating oh, wait. 666.66. I see an A in there. It should be ohms. Yeah, exactly. Okay. Okay. And that same person who put the 666.66, can you tell me what you got for your Norton equivalent circuit for the I and the R? I don't got omega on my keyboard. So when in older software where you didn't have access to omega, you would just write OHM afterwards, which would get confusing because you'd have a little O over there and you're like, oh, is that another 0? So what did you get for the Norton equivalent circuit? 7.5 milliamps. Yeah, okay. 7.5 milliamps, and you got you should have gotten the same resistance. Okay, so going by what I said earlier, we should just be able to apply Ohm's law to this, and we should get 7.5. Is that true? Let's take 5 volts and divide it by 666.66. I'll put my calculator over here, and we'll do 5 volts divided by 666.66. And look at that. We got 7.5 milliamps. Okay, so source transformation works. Very cool. Yeah, 7,500 microamps, same as 7.5 milliamps. Cool. Okay, so multiple verifications for our lab. You should have gotten the same current and current through the load resistor and the same voltage drop across the resistor as you did in the Thevenin equivalent circuit, as well as the Norton equivalent circuit. And then on top of that, now that we know that this is referred to as source transformation, which will become more useful next class when we go over Millman's theorem. It works here as well. Okay, so kind of cool. Okay, are there any questions about source transformation? This is a pretty easy, quick thing to cover. I think just knowing that you can do this and knowing that, you know, you can jump back and forth between these whenever it suits you best, and knowing that the name is source transformation is good enough. Okay, so let's jump to another topic. And this one's another one of those simple things that ends up being quite useful. In fact, this one might be very useful for you guys in the future, because a lot of times you end up working with sensors, and this is applicable in this case. And I'll do a demo of that. So let's go ahead and talk about this topic. What we are going to cover is the Wheatstone bridge. Okay. Now let me go ahead and just draw up what this circuit looks like. And I'm going to go ahead and refer to this node as being point A. And this point as being B, and apparently I'm not very good at drawing diamonds. Okay, now, when we mentioned about bridges last time, we did delta Y conversions, and I kind of introduced at that point what a bridge was. A bridge was just having two parallel branches where the center of both parallel branches end up being connected to each other some way. Now, in our case, for the Wheatstone bridge, the way the two center points are going to be connected to is with a voltage meter. So I'm going to go ahead and set this to V. We're going to take the positive side. Let me draw this in with the red. Going there, and we're going to take the minus side. And so our multimeter is the one responsible for creating the bridge between these two parallel branches. Okay, and I've denoted an A and a B. Now, I'm going to have to label some of these resistances. So let's go ahead and let's say our voltage source is V sub S, and over here is R1, and over here is R2, and up here, we're going to call this RX. You'll see why in a minute. And over here, we're going to have a variable resistor. So we're going to have something that we can change the resistance value of it. And we always denote a variable type of component by just putting a diagonal arrow through this. And we're going to call this R sub S. Okay, now let's go ahead and let's talk about R sub S a little bit. This is going to be our variable resistor. Oh, my face is covering this up. Let me move myself over there. Variable resistor And I'm going to call this variable resistor standard. The idea is that we're going to be able to change this resistance. We're going to know what value it is. Okay, so the standard part just means we can change R and know the value. Now, not a bad idea to now talk a little bit about a variable resistor. Now, the most common type of variable resistor is the potentiometer. And I have several different examples here. Okay, so here is a variable resistor. It's actually a little tin can, and inside, when I turn this, there's a little wiper that sweeps across a resistance and allows me to change what that resistance is. Let me go ahead and draw what that looks like. Okay, and let me grab a couple of different types over here. There's a pot, here's a pot, this is a pot, this is a pot, this is a pot, this is a pot. These are known as trimmers. So let's also write down potentiometer or trimmer. Usually when you say trimmer, you're referring to a pot that has more than one turn. Over here, if I turn this all the way to the left, I can't go any more. And if I turn it all the way to the right, I can't go any more than that. And so if you look at the construction of one of these variable resistors, a potentiometer, it's physically constructed more like this. I made it too small. Let me erase both of these and put my third terminal in the center here. And so if you imagine that the shaft is actually poking out of the paper, and so between my left terminal and my right terminal, I have a fixed value resistance. So in this case, this says 5K up here. So between here and here, I have 5K. So this is known as a 5K pot. And as I turn this, the wiper slides across that resistor and gives me two different resistances, one between this terminal and the other one between these two terminals, right? As the wiper gets closer to this side, I will get less resistance between these two and more resistance between these two. And in fact, let me go ahead and let me hook up a multimeter. Yes, I have a lot of pot laying around. And by that I mean I have a lot of potentiometers. Let me get 2 meters over here. Yeah, for some reason, whenever I talk about pot, I just get a lot more interest and a lot more paying attention going on in class. I don't know why that is. Let's go ahead and set this. It's a 5K pot, so we should, I need to put this to the 20K range over here. In fact, now it might make more sense to put my picture down there. Okay, and we can see, and I need a little better lighting. That did not make that much difference. That's okay, we can still read the value. Okay, and over here, I'm gonna take my other multimeter. Set this over to resistance as well. Now I have too much glare. Okay, I guess we're just gonna let the camera do its thing there. Okay, and I am going to need okay, we're gonna take the grounds over here. And to make this easier, I'm using these little mini grabbers that I have connected to my multimeter. These are actually incredibly convenient. You can pick these up in a pack of 10 of them for cheaper ones on Amazon. And let's connect both of the black side of the probes to the center pin, and let's put the reds on the outer. And I should have it such that the multimeter on the left is reading between the center pin and the far left, while the multimeter on the right is reading between the center pin and the far right one. And if I take this and turn, I'm gonna have to do this from the top here. Okay, check that out. As I turn this all the way to the left, I get 4.7 ohms, and I get 4.7K over here. This is 5K and almost 0. Let's go ahead and let's crank this. I'm gonna try and put this kind of in the center. Crank that a little to the left. Okay. About 2.3K ohms on the left and 2.3K ohms on the right. Okay, both of those should add up to roughly about 5K. I do have some longer cables over here, and I'm kind of pushing current through both of these to take the measurement. You're not going to get the exact value. As you've kind of noticed, components have tolerances. Components are not perfect. And so now it's like our terminal over here is in the center, or I should say the wiper is in the center. And then as I crank that to the right, okay, now you can see the resistance on the right multimeter is going down while the resistance on the left multimeter is going up. So very clever and useful arrangement. Whenever you have like a volume knob for something, you'll see this becomes very valuable to have a changing resistance. Okay. Now that's one type of variable resistor. I'm going to use both of those multimeters in a few minutes again. Okay, so you can kind of see this arrangement as reflected in those multimeters. What do the pins on the pot correlate to again? Yeah, so the far left, you know what I did not measure was the resistance from the far left pin to the far right pin. So let me go back to my 20K range of measurement over there, and let's go ahead and go on the two outer terminals. So I'm going to go from the far left and the far right. And you can see I have 4.87K, and it doesn't matter how much I turn this. That's a fixed value, right? Because nothing is changing. This is just staying as a constant resistance of 5K. The wiper is where you get that variable again. So those are my 3 pins right there. It's lined up perfectly with the image. Okay? So very cool, useful component. Okay, and all of these are essentially variations of the same thing. Little smaller, 3 terminals, and this one again only goes, almost 1 full rotation. Same thing with this. This is a little more of a sleeker profile. You kind of have to use a screwdriver to get in there to do the turning. And then you get these trimmers, and a trimmer is the same thing, except you can do multiple turns. So you can really dial in a very specific resistance with trimmers, because I can turn this about 10 times. So with 10 times. So the construction of this is physically quite a bit different than this. This is more of a screw terminal that slides up and down. Where this one over here is just simply a wiper that goes across. Okay, so those are all variations of the same thing, potentiometer or trimmer. I'm going to use, let me say what I said before, variable resistor. All of these fit that bill of being a variable resistor, but I cannot know what the value is unless I take it out and measure it. Okay, but if I have a variable resistance standard, I should be able to change the resistance and know what that resistance is without having to take it out of my circuit and measure what that resistance is. So let me put all this pot off to the side. Okay, and I'm actually going to put these all back into their home. And I need a different type of resistor. I need something that I can know its value. Welcome to the resistance substitution box. Okay, this is known as a decade resistance substitution box. And what it does is it has all of these different resistors that are wired in series with each other. And the way it works is when all these switches are down, all of these resistors are shorted out. So I actually have a direct connection from one side to another. Okay, let me actually show that with a multimeter. And for this one, I'm going to use a ranging multimeter, because I'm going to go all the way from ohms, single ohms, 1 ohm, all the way up to a mega ohm you can do with these resistance substitution boxes. In fact, let me zoom out a little bit. There we go. And by zoom, I mean physically move my camera further away. And let's go ahead and set this up so it is reading ohms. And I'm going to need to go from, the resistance that this substitution box provides is between these two terminals. So I need to connect those to these two terminals. And I have cables that go from these are called banana jacks and banana plugs. In fact, here's what a banana plug looks like. Here's a banana jack, and the two can, do that with each other. Okay, let's go ahead. And I'm going to get a cable that has banana plugs on both sides, so I can very conveniently go from black over there to black over here. And in this case, color does not make any difference. Copper does not care what color the plastic is on the outside. And then I'm going to go from my volt measurement. I hope that's going far enough to actually make connection. Not sure if I've tried this before. Okay, looks like it is working. And it looks like we have 43.3K. Why do I have 43.3K? Well, let's see. Right now I have the 40K up, and I have the 3K. No. 40. Oh, I have a 2K and a 1K. That's up. These two switches are up. So I have 42, 43K. And where's that 0.35K coming from? All of these are down. Okay, that 0.35 must be coming from wires or some error in the measurement accuracy. These are 1% resistances. But let's put all of these down. Okay, everything's down. Okay, I have 0.2 ohms from here to here. That's being measured by my multimeter. Cool. And let's go ahead and let's flip the 1. I get 1 ohm. Now, our 0.2 was the error. And I don't cover in this class, I don't go over error that much. If you haven't noticed, I don't go over error in components. In electrical engineering classes, they got to spend a lot of time dealing with the error. As computer engineers, we only have 2 classes to cover fundamental electronics. So if I ate up, 20% of the time dealing with these errors, I would not be able to have as much information in these classes. So I kind of try to teach it from a little more of a fundamental idealistic point of view, but we just recognize that there is some error, and that's coming from the measurement from the multimeter, from some resistance in these wires. Inside this box is a bunch of wires as well. There's going to be some error, and it is quite small. Okay, so let's flip up the 1. So what I just did now, all of these resistors that are built into this box are now disabled, except for the 1 ohm. I unshorted the 1 ohm. So let's actually look at that on paper. Okay, and what I'm going to do is I'm just going to zoom in on the 1 ohm. The 10 ohm and the 100 ohm. Okay, now if I have a switch across each one of these, okay, I think now it's real easy to visualize. So the switch being down is actually all of these being closed. And so I'm bypassing these 2 outermost resistances. Right? Because when any one of these switches becomes closed, it disables or shorts around this resistor, effectively removing it from the circuit. So that's what's going on inside of this resistance substitution box. I'm leaving only the 1 ohm resistor working, and all other ones have been disabled all the way from one side to another. And I didn't draw in the resistor over here. Just assume we have a 10 ohm and a 100 ohm that's in parallel with a short. And so they have effectively disappeared from our circuit. So whenever I flip the switch up, I'm enabling those resistors. And we can see that in this resistor substitution box and on the meter at the same time. So if I go ahead and they're all shorted out now, so I have a direct short across from this terminal to this terminal, I open up the switch and now that 1 ohm is allowed to operate, and so I get 1.2 ohms, 0.2 being my error. Let me go ahead and enable my 10 ohms. Now I have a 10 ohm in series with 1 ohm. I get 11 ohms. Okay, let's go ahead, turn on the 100 ohm, and now I have 111 ohms. Okay, and if I turn this one off, I should get 110, and if I turn the 10 off, I should just get 100. And I can do this in this resistance substitution box, and I can make any value between 1 and 1.111 mega ohms if I had all of these enabled. So if I wanted to make 5 ohms, turn on the 1, turn on the 2, turn on the 3. That actually makes 6 ohms. Let me do 5 ohms. Turn on the 2, turn on the 3. I now have 5 ohms. If I wanted to make 9 ohms, I can turn on the 4, 5, 6, 7, 8, 9 ohms. If I wanted to make 10 ohms, I can do that, turn all of these on, or I could just turn on the 10 ohms. And so I can create any value I want. If I want the value 666K, or actually 666 ohms, similar to the answer that we got from lab. But let's just say it was in K. So 400K, 600K. And then I want 600 ohms. So we do 4, 5, 6 again. What just happened there? Oh, I'm in the 100K. Sorry, the range is out of range. I need to go with the 40 and 20K. Now I get 660K, and then if I wanted to do next 4 and that, and I should get about 666K, a little bit of error thrown in there in the measurement. Okay, so that's kind of the nice thing about this resistance substitution box. I can change the resistance to any value I want, and I can know what that value is. Okay, and I'm going to use this for the Wheatstone bridge that we just looked at. We just did a sidetrack, a little segue to talk about variable resistances for a minute, and I covered potentiometers, trimmers, and resistance substitution box. This is a little bit of an older type of piece of test equipment. They're not as common anymore, but they still have value inside of the electronics, inside of any electronics lab, and I use it quite regularly. Okay, so let's get back to this Wheatstone bridge. Okay, so we've talked in length about this variable resistor that we can know its value. Okay, and we're going to measure the voltage between one side and the other side. Now, this Rx, the reason I labeled it as Rx, this is going to be an unknown resistance. Okay, we're going to put something in that we don't know what the value is. We're just going to put some unknown resistance, something we want to measure. Let me put that in there. Resistor, resistance. We want to measure. Okay. And now we have these two resistors on the far left side, R1 and R2. We're going to refer to this as the ratio arm. Create the ratio arm. Okay, that's what this leg is referred to, this side of that parallel branch. Okay, and now if you notice, what this Wheatstone bridge is really consisting of is two voltage dividers. And we've talked about this voltage divider before. We've talked about this before. When you have some voltage and you want a different voltage out, you can create a lower voltage by dividing it down using two resistances, R1 and R2. And we solved this before, and we wrote out what that equation ends up being for R1, for V out in terms of R1, R2, and V in. In fact, V out is going to equal V in times R2 divided by R1 plus R2. Okay? So if I had 10 volts and I want to make 5 volts out, as long as I pick R1 and R2 such that they are the same value, I will get 5 volts out. And I can go ahead and solve that for you real quick over here. 10 volts, 100 ohms, 100 ohms, and V out should be equal to 100 times 10 divided by 200. Well, what does that end up being? Let me pull up my calculator over here. So I said 10 times R2, which is 100, divided by R1 plus R2, or 200. I get 5 volts out, right? So, and you can change the ratio of R1 and R2 to produce any voltage that you want under 10 volts. Okay, and you just solve this equation for that. You pick one of your values. You fix, R1 to be 100 ohms, 200 ohms, whatever you want, and then you solve for what the other resistance would be for a desired voltage out. So this is a very fundamentally useful circuit, and it appears here twice. We have R1 and R2 forming one voltage divider between points A and B. And we have Rx and Rs forming another voltage divider over here between points A and B. And if you remember, parallel circuits will have the same voltage across them. So whatever Vs is will be across this voltage divider, the R1, R2, and Vs will be across Rx and Rs. Okay, so we have two voltage dividers with the same voltage across them. So we can go ahead and we can apply this equation twice for the voltage between this point and the voltage between this point. So let's actually call this D and C. Okay? And actually, let me do this in blue. So I can kind of emphasize these two different voltages. We'll call this one D, and we'll call this one C. Okay, so we actually have two different voltages here formed by two separate voltage dividers. And let me get another sheet of paper so we can go ahead and apply our voltage divider equation to both of these. Okay, so we're going to get a V sub D. And what is that going to be equal to? Well, we're just going to apply this voltage divider equation. Instead of having V in, we're going to have V sub S. So it's going to be V sub S times R2 divided by R1 plus R2. Okay, so that easy. And if you're curious about this equation, you can just solve this using your basic rules. The current flowing through all of these is V in divided by R1 plus R2. Take that current, multiply it by R2, and you get this equation. So this is a very simple yet very powerful circuit. And it ends up being so incredibly useful and valuable that we just tend to memorize this equation because it just pops up left and right. There's no point in me not remembering this equation. There's equations we don't really have to remember that much. And I usually try to do a good job of telling people, like, yeah, this you come across, once a year, once every couple of years. You don't have to remember this, but this is one of those that you encounter on a, every other day kind of a basis. If you're an electrical engineer, you see this 20 times a day. Okay, let's go ahead and do the same thing for C. Okay, VC is going to be equal to, well, what's V in? V in is our V sub S. What's R2? R2 is RS. And what's R1 plus R2? Well, it's RX plus RS. Okay, so now we have two equations that refer to the voltage at D and the voltage at C. Okay, now let's go ahead and now say if we have a voltage of 0 on D and a voltage of 0 on C, then we have no voltage between these 2 points. If we have a voltage of 1 at D and a voltage of 1 at C, again, we have 0 volts between these 2 points. As long as they have the same voltage at these 2 points, we get a 0 volt drop across this bridge. When that happens, when V sub D equals V sub C, we say that we have a balanced bridge. Okay, so the bridge is balanced when these two voltages are equal to each other. And if these two voltages are equal to each other, then they must be at the same voltage. Now, we can go ahead and use that to measure Rx by changing this resistance over here. Let me address a question. And typically, do we want a balanced bridge, or are there times when we want a voltage drop between? There are times when both are useful. Okay, and I will actually, the demo that I do will show both of those cases. Okay, now let's go ahead and we know, let's just operate on this from the perspective that this is what we want. We want it to be balanced for now. Once we understand what happens when this is balanced, then we can go ahead and look at when it's desirable to not have it balanced. Okay, so it is balanced when both voltages are equal to each other. Now, that means let's set both of these equations equal to each other. Let me do this in black. So now we're going to take V sub S times R2 divided by R1 plus R2 and set it equal to V sub S RS divided by RX plus RS. Okay. Yes. Okay, so now this situation is when balanced. And we can go ahead and start removing some things from here. First off, we can divide both sides by V sub S. The voltage applied between points A and B does not matter because it's only the ratio of R1 to R2 as compared to the ratio between Rx and Rs, right? When I pick R1 and R2, I get a voltage here. And if I pick Rx and Rs, such that they have the same ratio, I get the same voltage here. So it's independent of our applied voltage, and you can see that in the equation right here because I can cancel out my V sub S's. So we get give me 1 minute here. We're going to get R2 divided by R1 plus R2 equals Rs divided by Rx plus Rs. Okay, and then we can use this to figure out what Rx is by setting Rs such that we get 0 volts between D and C. So let's go ahead and let's do this. So what I have here is a little breadboard, very tiny breadboard, kind of cute actually. And let me crank down the, it's getting hot. It is getting hotter in the office. Okay. And let's go ahead and let me include a picture of what we're going to have. Now, I've picked these two values to be 12K for R1 and R2. Our X is going to be our unknown. And RS is going to be my resistance standard. And I'm going to just use, let's just use 5 volts for this. Okay, so what I have here is 12K, and I have 12K over here. Now, for my unknown resistor, I'm going to just pick one of these resistors, and I'm going to put it into the breadboard. such that one side is connected to the top, this point right here. I have my 12K, my other 12K is connected to it. And over here is where I'm going to connect up my resistance standard. Okay, and I'm gonna need 5 volts and some connections for this. So let me first connect up my resistance substitution box. So this is just gonna act like my variable resistor here. I do want to bring this in from bottom right here. We're going to connect one side to that resistor, and we're going to connect the other one right there. Okay, so now I have our bridge circuits been created, and I'm using my resistance substitution box for that R sub S. Now I'm also going to need power. So I'm going to, off camera here, connect up my benchtop power supply. And my benchtop power supply is going to come out to these two black and red leads as well. So I'm going to connect these on the top and bottom of my bridge. Okay, and now I need to measure the voltage from one side of the bridge to the other side of the bridge. It's getting tricky to fit all of this on camera. Okay, we'll see if we can do something about this glare when we start getting some values. And I'm going to do the same thing. I'm going to use some of these mini grabbers to measure the voltage between the two. Okay, so, and let me see if I cut the light. Okay, that's a bit better. So, okay, just to reiterate connections, I have positive and minus of my 5-volt source connected to the top and the bottom of the bridge. I have my multimeter measuring voltage between the left branch and the right branch, and I have this substitution box acting like my resistance standard between the right side of this unknown resistance and the bottom here, and then I have an unknown resistance over here that we want to measure. Okay, so we want to measure what the resistance of this unknown is. So what I'm going to do is I'm going to turn on my voltage source, and notice we are at 2.28 volts. My goal is to change my resistance substitution box such that the voltage at V sub D is the same as the voltage from V sub V sub C, okay? So I want to set both of these voltages to be the same. So I need to change my resistance until this reads 0 across. Does the display... I am checking to see right now if my multimeter lights up on the display, and it should. I have a light on the top of it. Yeah, that's not working. Apparently the backlit display is not working. Let me see if maybe... I can get a little more light on it. Actually, you know what I can do? I bet that's a little better. Okay. So right now I'm reading 2.3 volts, and I said I want to make this 0. So what I'm going to do is I'm going to start changing my voltage, and let's see which direction change my resistance and see which direction the voltage goes. So right now I'm at 1K. Let's flip on the 2K and see if that goes up or down. Okay, it went down. So I need to make my resistance higher in order to make this go to 0. Let's go ahead and now turn on the 3K, and we're going to turn this resistance substitution box into a total of 6K. And it looks like we're getting closer. Okay, let's turn on the 4K as well. We're at 0.9. Okay, let's turn on the 10K over here. Ooh, we got really close. We're 0.13 volts. Let's turn on the 20K. We just went negative. We went in the wrong. We went past where we want to be at. So let's actually turn all of these off. Okay, I'm still too high. Let's turn off the 10. Okay, we're back to 0.139 volts. Let's turn off the 20 and turn on the 30. Okay, we went too far in the other direction. So it looks like 20 is looking good, and adding 10K to that is too much. So I think we need to move down the decade to messing with the K's over here, the 4K and the 3K. So let's do 4K. We overshot it. Let's do 3K. We overshot it. We went to negative again. Let's do 2K. Okay, we're getting close. 2K. And I'm at 0.017 volts. I'm almost there. Let's add 1K to that. Too far. Okay, let's start messing with the hundreds now. Let's do 400. Oh, close, but we did go over. So let's turn off the 400, turn on the 300. Hey, I'm exactly at 0 volts. Okay, so let me write down what I have on right now on my resistance substitution box. I have 20K. I have 2K. And I have 300 ohms. And that's it. All the other ones are off. Just a 300, a 3K, sorry, a 2K, and a 20K. All others are off. Okay. Let's go ahead and let's take a look at that. So I have 22.3K, or in other words, 2, 2, 3, 0, 0. 20K plus 2K plus 300 ohms. Okay. Now, this was an unknown resistor. I didn't know what this value was. I'm using the bridge in order to measure it by testing it against known resistances. That's what we were doing in this bridge circuit. So let's read the value and see what we actually had. So 22300 comes out to be red, red, orange, well, actually, this is a 3 color code, so I have to do this with only 3 colors. And so red, red, and 3 zeros come after it. Looks like I'm going to lose this 0.3K. And red, red, orange, I don't know if you can see, is the correct value. So we did measure the correct resistance. This 300 ohms was error. Now, is that tolerable? Yes. Okay. Because this resistor is a 5% accuracy resistance. That means 5% of its intended value plus minus that. Its intended value was red, red, orange, which is 22K. And that times 5%, 22,000 times 0.05 means we can be plus minus 1,100 ohms and still be within spec. And we measured an error of 300 ohms. So we're well below that. Okay. So this bridge worked for what we intended to use it as. Measured an unknown resistance. Now, what I didn't tell you was this Wheatstone bridge was invented in the 1800s. And in the 1800s, they did not have nice multimeters that could measure resistance. In fact, let me pull up a multimeter, a quote-unquote multimeter from this era. back in the early 1900s, the best you could get was just a voltmeter. Or actually an ammeter, because this analog needle was driven by a little electromagnet, and as you put more current through it, the needle would move. And so you would measure current and hence infer voltage using this property of this. And this is all you had back then. So how do you measure resistance? A bridge is a good way to do it. Now, it feels like a moot point because you're going to tell me, well, we live in the 2000s and I have a multimeter that can measure resistance. So why is this bridge even being talked about? Why are you wasting my time talking about an 1800s technology? Here's the reason. We can use this bridge so that a circuit can measure resistance. We can use this bridge for measuring different unknown resistances from something like a sensor. And that's exactly what I have down here. This little black thing is actually a temperature sensor. And a temperature sensor just varies resistance based off of temperature. You can also do little light sensors. Cadmium sulfate cells are little resistors that change their resistance based off of the amount of light they receive. In fact, many sensors just change resistance, and it's up to our circuit to measure the difference in resistance. Okay, so before I talk about these temperature sensors, I want to give a minute for any questions about what we've done thus far as this bridge circuit. Yes, the sensor would be in place of our X, but we would not use a resistance substitution box. We would not use a variable resistor. We would actually fix this to be another fixed known value resistor and then just use the voltage drop between both to figure out what the value of our sensor is. So that's actually what I'm going to do next. But does anybody have any questions about this resistance substitution box, the bridge circuit we've looked at thus far? It is a very simple circuit, and we should actually be able to understand this very easily given what we've learned thus far. Okay, so we are definitely running out of time here. So let's go ahead and let's, in place of our resistance substitution box, I'm going to put a known value resistor. And in place of my unknown resistance, I'm going to place my sensor. I'm going to apply my voltage to the top and bottom. I can run this off of 5 volts, I can run it off of 9 volts, I can run it off of 3.3. It doesn't really matter, because I'm just going to compare the ratio of the voltage difference between point C and point D. Looks like we are sitting at 2.49. Now, if I change the temperature, our voltage is going to change. Why are you not cooperating with me now? Because I'm measuring it incorrectly. I put this on the wrong place. There we go. Okay, so somebody had previously asked the question, is there a time when I want this bridge circuit to be unbalanced? Yeah, absolutely. If I'm using a Wheatstone bridge as part of my sensor circuit, then I want it to be unbalanced, because that unbalance is what's going to allow me to take the measurement of my unknown resistor, my sensor. So now let me change the temperature. There we go. So now I'm just insulating it with my fingers, and so it's kind of measuring my temperature between my fingers. And if you notice the voltage is going minus, well, because I have my probes swapped. In fact, probably easier for me to just change it on my multimeter. There we go. And now, so at room temperature, I'm at 0.22 volts, 0.2, 0.19. You can see that temperature is dropping. It does take some time for the transducer, the sensor, to come up to a given temperature. Okay, and then let me insulate it again, and you can see that voltage drive up again. Okay, so with a changing voltage, I can construct my my embedded system like a 262 type application to take a measurement of this sensor. And it doesn't have to be a temperature sensor. I can use any type of sensor that changes its resistance, which many of them do, based off of, well, whatever it's measuring. So let me use a light sensor. So what I have here is a little light sensor. This is known as a cadmium sulfate cell, and these are great for when you want to if you want to make like a line following robot. You can use this to detect black versus white, because white reflects more light. You can use this as a motion sensor. So your motion sensor lights, they all do this, and they usually use something like this. And in place of this, so again, 0.38 volts, and if I cover it up, you can see how quickly that changed to minus 1.58. Again, my multimeter is just reversed, and I could probably do a better job of setting up this fixed value resistor over here so that it starts at 0 and goes up to some value. You can adjust the range of this. In fact, if I wanted to, I could also use a potentiometer. You're going to love this one. Let's take this potentiometer and now I can use my variable resistor. Oh, I think I picked too high of a value. I'm going to need something smaller. This was 500K. Yeah, that's definitely too high. Let's go with 10K should probably do it. Oh, what did I just do there? Oh, I took off my... There we go. Beautiful. Okay, so I have that at almost 0. And then now I get a very extreme difference in voltage. See that? So I'm changing by 2 volts. Or almost 2 volts. And I use this variable potentiometer in order to, we would call that nulling, where I set its baseline to be about 0 volts for my intended application. Okay? So the bridge circuit for measuring an unknown resistance is kind of a moot point because we have multimeters that can do it very well. Though if you wanted to very accurately measure resistance, a Wheatstone bridge can do it better than your multimeter if you set it up right. But you can use it as a very fundamental good starting point for creating a sensor circuit. Okay? So that's where the Wheatstone bridge is going to shine these days, is for constructing sensor applications. Another great benefit of our Wheatstone bridge is resistance changes with temperature. Well, since I'm only measuring the ratio between my 2 voltages, as temperature goes up, these resistors change their resistance slightly as well. So we can assume that the whole system changes temperature at the same time. That's going to help to negate some of those temperature effects of our sensor circuit. So when you're trying to create a good sensor application, a good sensor circuit for an embedded system or FPGA type project, a Wheatstone bridge is a great starting point. It might not be the end-all be-all, but it's definitely a great place to start until it's not capable of giving you what you want, until you run into a problem with it, and then there's more advanced techniques to work off of. But this is a good starting point. Okay, so that's what I wanted to cover today: source transformation and look at the Wheatstone bridge. This might be one of the more useful circuits that we've seen till now. A lot of what we've been looking at has just been techniques for solving circuits, but we couldn't get here until we learned those previous things. Okay, so I'm gonna go ahead and end class now, and I'm gonna hang out, and if you have any questions, I'm happy to answer. We're definitely into lab time right now. There is no new lab for today, just that previous Theven and Norton lab that should have been submitted by today. So okay, I will see you guys next time.